Welcome everybody to our next unit. So we're going to work on unit 3 today. It actually only covers one chapter, chapter 6, and that's because chapter 6 is a little bit of a bigger chapter. It also covers some seemingly random topics, and so I just want to make sure that we have an opportunity to really focus on what chapter 6 is talking about, because it really is kind of the basis of why ultrasound works and the way that it works. So I want to make sure that we get ample time to study this chapter and make sure that we understand the concepts that go into it. So this chapter is going to discuss media and sound. And when we think about the sound being going in the body, we've spent a lot of time talking about sound entering the general term soft tissue. And we know that soft tissue travels at 1540 meters per second. But we also know that that's the average of all of the tissue that the sound may be encountering. So it goes through bone, it goes through muscle, it goes through urine, it goes through blood, it goes through tons of different types of media in the body. And so with that, what ends up happening is that as that sound encounters the different types of media, some of the sound is reflected. And that's 100% what's happening. That's why we get pictures from ultrasound. We're getting the echoes or the reflections of the sound after it interacts with something. The strength of that sound then gives us the echogenicity on our screen, and that's why we can tell heart walls from the middle of the chamber, liver from the gallbladder. We get all this information based on the reflection that occurs. And something to keep in mind is that some of the sound is reflected, most of it is going to keep traveling through. And that again is then why we get to see further into the body. If all the sound got reflected right away, then we'd only see like a centimeter into the body and that'd be it, and ultrasound would be worthless. So remember that as we're talking about sound traveling through the body, remember that that sound energy is coming in, just a tiny itty bitty fraction is going to be reflected back so we can get that reflection information. More is going to keep traveling through as that transmitted sound keeps going. Some more of that's going to reflect back so we can get more information. It's going to kind of keep doing that until it attenuates completely or gets weak enough where we can't see anymore. Or maybe we've even just reached the bottom of our field of depth that we're requiring. So again, the whole reason that we have pictures is because sound is interacting with media. That media is causing reflections, and the machine is then processing those reflections for us. Remember too then that sound weakens as it travels. We call that attenuation. So as the sound travels through the body, it is not as strong as it was when it left the transducer. And remember that we learned sound travels in straight lines, but as it interacts with different media, it can change directions. It'll change in a straight line, but it does change directions. So first we're going to talk about comparing signals. And there's a few terms that go along with that. So we just talked about attenuation. That attenuation is the weakening of the sound waves as they propagate through the body. So the sound gets weaker, gets less strong, the amplitudes go down, the intensities go down as the sound travels through the body. Amplification then is the strengthening of the signal. And amplification usually happens within the machine. So it's not something that we're doing in the body, it's not something that the sound is interacting necessarily with the media. It's those reflections, remember they're very weak, are coming back to the machine, and the machine is going to then amplify them or make them stronger. And we'll learn in another chapter why that amplification needs to happen, but basically we're just making the signal stronger so the machine can manipulate them and calculate and transform them into what we need to get our picture on the screen. Another concept with comparing signals is the idea of decibel notation. And so this is a tool that just helps us to describe either attenuation or amplification. And this is going to be comparing an original signal to a new signal. So in attenuation, let's just say, for example, our original signal was 50 decibels. Attenuation then would cause it to go down to 30 decibels. It would cause a weaker signal to be produced. Decibels must have a new and an old. They are a comparison or a ratio of two signals. Amplification then, if we talk about decibels and amplification, if we start at 50, amplified that then up to 60, up to 70, we make it bigger. And then logarithms, which is what we're going to talk about next, is a number rating system that decibels are based on. So first we're going to learn about logarithms, what they are, how we use them. We're going to see how that applies to decibels, and then we can better discuss attenuation and amplification because of it. All right, so logarithms. The whole reason we're learning logarithms is so we can talk more about decibels. Logarithms are a way to rank numbers. It keeps numbers from getting extraordinarily large, but it still shows that there's a great magnification between them. And we'll talk a little bit more about that as we go through the logarithms. So let's just first get down to the nitty-gritty math of logarithms. So when we say logarithm or log, without any other annotation, we are basically saying that it has a base of 10. It's a log base 10. And what that log base 10 is basically saying is how many tens does it take to make a number. So I've got our example here. We know that 10 times 10 equals 100, right? So it takes two tens, 10 multiplied by 10, to equal 100. Therefore, our log of 100 is 2. Let's look at another example. 10 times 10 times 10 times 10 equals 10,000. So it takes 4 tens multiplied by one another to get the number 10,000. So therefore, the log of 10,000 equals 4. Let's see if we can look at some other examples here on the whiteboard. So remember we said log of 100 is going to equal 2. And that was because it was 10 times 10 equals 100. It took 2 tens multiplied by one another to get to 100. Another way we can look at this, we've talked about powers of 10. So we know 10 squared also equals 100. So all of this is kind of related together. We're building layers onto this. So that is our first example. Log of 10,000 we said was 4, and that was because it took 4 tens multiplied by one another to equal 10,000. Another way we can do this, just count these. 1, 2, 3, 4. There's 4 zeros. 10 to the 4th equals 10,000. So you're kind of seeing how all of these are related. How many tens does it take to multiply against each other to get this number? Another way we can say it then too is 10 raised to what power equals that number. And so we know 10 to the 4th log is 4. All right? So again, we're just basing numbers on the powers of 10, the metric scale. We're using all of this to our advantage. Let's try just one more example here. What if we say, what is the log of 1,000? So remember, we have a couple tools. We can count the zeros. We can think back to our powers of 10. 10 raised to what equals 1,000? Or can we write it out and do the math? So we are saying that it will take 3 tens multiplied by themselves. So 10 to the 3rd, 10 times 10 times 10, or count those zeros, all gets us to 1,000. So the log of 1,000 equals 3. So that's basically how we're going to figure out logs. It gets a little bit trickier when we start to talk about numbers that aren't 10, 100, 1,000. It gets a little bit trickier. And again, it's just asking the same thing. What is the log of just another number, let's say 12. Now this gets tricky because we can't just look at that and be like, well, it's 1/10 and partial of a 10. And so I'm just going to show you on my calculator here. And again, you're not going to have to do this because remember, all of our stuff that we're talking about is always pretty much based on tens. So we're not going to have to do this as much, but I just want to show you on the calculator if you have a question like this. So if I slide over, I've got log, and I can just put 12 in there. So the log of 12, according to my calculator, is 1.079. And remember, that's the same as saying 10 raised to what power is going to equal that number. So if we take 10 to the 1.079 exponent, we'll get about 12. So let's double check that. We can take 10, raise that to 1.079. Look at, we get 11.99. Might as well be 12. All right. So again, we're trying to figure out 10 raised to what power is going to equal the number that we're asking for. So here I have a nice little chart that kind of shows us those logs raised to their power. And what I want to point out with the logarithms is a scale that you're actually probably already familiar with. If you've ever heard of earthquakes and the Richter scale being used, the Richter scale is actually log based. So this kind of shows us how we compare numbers that are on a logarithmic scale. And remember, decibels are logarithmic, so this is going to apply in a little bit. But looking at this example, if we have an earthquake that has a magnitude of 5 on the Richter scale, and we compare it to another earthquake with the magnitude of 2 on a Richter scale, we're not saying that that first earthquake is 3 bigger or 3 times bigger. We're actually saying that it's 1,000 times bigger. And that's because for every number we go up on our logarithmic scale, we are actually increasing by 10 times. So remember, we were at 5 and we're comparing it to an earthquake of 2. So when we increase 2 to 3, we're 10 times bigger. And when we increase to 4, we're another 10 times. And then when we go to 5, we're another 10 times. So it's 10 multiplied by 10 multiplied by 10, which equals 1,000. So 5 is 1,000 times stronger than 2 in a logarithmic scale, such as the Richter scale. So just as a reminder then, when we're trying to determine the logs of numbers, we can count the zeros if we're using our handy dandy knowledge of the metric system and the powers of tens. It gets a little bit trickier when we need to talk about numbers that aren't based on it. And we're going to talk a little bit more about that when we get into decibels. So decibels. These are going to be used to report relative changes. Remember, we have to have a starting point and a finishing point to really talk about the decibel change. So we need 2 intensities to understand decibels. Because we need those 2 intensities, we're actually getting a ratio from the numbers that we're looking at. And in the end, we've talked about this already, this is going to be based on a logarithmic scale. So keep these 3 things in mind while we're talking about decibels. When we increase the decibels or have a positive change in decibels, we are amplifying the sound or the strength of the signal. Opposite to that then, if we are decreasing the decibels or have a negative change in decibels, then there is attenuation or weakening of the signal. Knowing those 2 things, this chart right here is going to be gold for what you need to know about decibels. So what this chart is saying, when our decibels go up by 3, so say we go from 27 decibels to 30 decibels, when we compare those two signals, we know that the new signal is 2 times as strong than the first signal. Similar to that then, if we increase our signal by 10, say we go from 50 decibels to 60 decibels, our new signal is now 10 times stronger. So remember, this is based on logarithms. We're not just increasing by our true number, we're increasing by a multitude of number. When we decrease our decibels by 3, so we go from 30 down to 27, that new signal is now half as strong. And if we decrease by 10, it is now 1/10 as strong. So let's kind of reiterate some of this. Let's look at the math on it. So let's say we have a original signal that is 30 decibels. If we increase that to 33 decibels, this new signal is now 2 times as strong as it originally was. Say we increase that signal now to 40 decibels. This one is now 10 times as strong. So it's not just like a plus 10 bigger, it is 10 times as strong. It's massively stronger than what it was at 30 decibels. So this was by adding 3 and by adding 10. What happens then if we subtract? Let's go down to 27 decibels. This new signal now is half as strong as it originally was. And if we subtract 10, go down to 20 decibels, it is now 1/10 as strong as it was. So when we add, we're amplifying. When we subtract, we are attenuating. Attenuation is assumed a negative. So if you see something that says the sound attenuates, know that you are subtracting. So again, just knowing this chart is going to be massive for you understanding how to calculate decibels on your boards and on your tests. So this is going to be a memorization thing. You'll get practice in your workbook with this as well. So now I have another chart, and you're going to be doing something very similar in your workbook as well, but I want to go through some of these examples so we can see how to do the math, how to calculate the decibel change, how do we know how strong it is, how do we know how weak it's gotten compared to the signals. So remember, whenever we're talking about decimals, we should be comparing an original decibel to a new decibel, and then we're going to talk about the amount of times that it got bigger or the fraction of the strength that it used to be. So let's again go back to the whiteboard and take a look through some of these examples together. So our first example had us going from 50 to 60. So the difference between these, we take 60 minus 50, we see that there's a difference of 10 decibels. And it's a positive 10 decibel change. And if we go back to our chart, maybe I should write that down here. Plus 3 equals 2 times, plus 10 equals 10 times, minus 3 equals 1/2, minus 10 equals 1/10. All right, so we can just go down to our chart here. We see that a positive 10 decibel change or difference means that the new signal is 10 times stronger. And that's all you need to know about changing from 50 decibels to 60 decibels. It is a 10 times stronger beam. Let's look at the next one. We have 50 decibels, and we are amplifying to 56 decibels. All right, this gets a little bit trickier. So now we know that there is a +6 difference in our decibel change. So let's go back down to our chart. We can use this +3 to help us figure out how much stronger this new beam is. So we have a +3 and a +3 basically, right? To get to that +6. Well, the first +3 gives us a 2 times stronger beam, and the second +3 also gives us a 2 times stronger beam. So we can do 2 times 2, and in the end, we figure out that the new beam is now 4 times stronger. All right, let's do another example. Again, we're starting out with 50 decibels, and we've increased or amplified our signal to now 59 decibels. There's a change of +9. So we're going to use that same idea. We're going to use our +3 to help us figure that out. So 1 +3, another +3, and a third +3 gives us our +9 total. So now we have 2 times stronger, 2 times stronger, and a 2 times stronger. So 2 times 2 times 2 equals 8. So the new beam is now 8 times stronger than the original beam. And remember, we've got to multiply these together. We don't just want to add them together. We need to multiply those together to get our 8 times stronger. All right, let's look at the next one. So we've gone from 50 decibels down to 40 decibels. So now we've attenuated, or we'll have a negative difference. So we have a negative 10 decibel change. Well, we can go down to our chart here, and we can now see that the new beam is 1/10 as strong as the original. All right, let's look at another one, kind of using our examples from before. So now we've gone from 50 down to 44 decibels. There has been a change of -6 decibels. So again, remember, we can break this down into a change of -3 and another change of -3, which would be the same as half as strong once, another half as strong. And because we multiply these together, our new signal is 1/4 the original signal. Okay, so I'm hoping that you're kind of starting to pick up on the pattern here. And you might be asking, well, what if we only had a 2 decibel change? Well, it's a thing that happens, and we could do the math on it. But again, we want you to understand the concept behind this, what's happening in general. You're never going to look at your ultrasound machine and be like, oh, I changed that 2 decibels. I now know that this is 0.1567 times weaker or something like that. That's not how it works. We just want you to understand that when you increase your power, increase your intensities, you're not just increasing it a linear number, you're increasing it by multiples of numbers. So let's jump down to another example. Let's say we had 50 decibels and we increased to 80 decibels. So now we've had a change of positive 30 decibels. And just like we did with the 3s, we can do the same thing with the 10s. We have a positive 10, a positive 10, and another positive 10 change. For each of those then, we are multiplying by 10 times as strong. We're looking at this one here, right? So now we have 10 times 10 times 10. Tells us our new signal is now 1,000 times stronger than the original signal. All right? So just, again, just using this chart that we've made down here, memorize this, write it down on your cheat sheet, write it down in your notes so you can refer back to it easily, is going to be golden for figuring out decibels and the changes that we see when we change the decibel. So when we talked about decibels, we talked a lot about attenuation. We know that when the strength decreases, when we go from 50 to 20 decibels, when we decrease our amplitude, when we decrease our intensities, we are attenuating. And we know that attenuation occurs as the sound travels through the body. Well, there are two things that determine the rate of attenuation, or why the attenuation occurs. The first one is that it is determined by the path length, or the distance that the sound is traveling. So if the sound has to travel more into the body, more distance, we're going to have more attenuation. So distance and attenuation are directly related. Secondly, we have frequency. And it's the same idea. The higher the frequency, the more attenuation that occurs. And so frequency and attenuation are also directly related. And so it's these two factors that determine how much attenuation occurs. So again, just to reiterate, path length is the same as distance or depth into the body. So the further the sound travels, the more it's going to weaken. And because of that, they are directly related. So more distance is going to equal more attenuation. And if you think about it, think about when you're scanning and say you increase your depth to 20 centimeters. Can you see all the way down to 20 centimeters? No, at some point we kind of start to lose signal in our really far deep field, right? And that's because of attenuation. There's just not enough sound energy to create strong enough reflections that can make it back to the ultrasound machine. So more depth means more attenuation. The further that sound has to travel, the more attenuation occurs. Now the other thing we see is that frequency also plays a big role in attenuation. The higher the frequency, the quicker it's going to attenuate. And we'll actually see some math on this in a few slides. So if you're using let's say a 3 megahertz transducer, that's going to get further into the body than a 15 megahertz transducer. That high frequency, the 15, that very high frequency is going to attenuate much faster, and it's not going to be able to penetrate into the body. So remember, we talk a lot about frequency and penetration. High frequencies are great for detail and very little penetration, where low frequencies are much better for penetration, but we start to lose a little bit on that detail. So what causes attenuation? There are three things that cause attenuation. And remember, attenuation means a negative change in decibels, going from 50 decibels to 40 decibels. We are weakening. So the three things that contribute to attenuation are reflection, scattering, and absorption. So let's take a look at each of those a little bit closer. So first we have reflection. So when sound is sent into the body, at some point, and actually very quickly, it's going to hit a boundary. It's going to hit some different sort of tissue. And when that occurs, sound is going to be reflected back to the transducer. Now we talked earlier that some sound gets reflected, but most gets transmitted. We have two different forms of reflection that occur. We have specular and diffuse. And reflection usually occurs when that structure, or the boundary that it interacts with, is a little bit larger than the wavelength of the frequency. And we're talking about 2 to 3 wavelengths. So specular is actually pretty uncommon in the body. It's not seen very often. And that's because a specular reflection requires a smooth boundary. So think about your mirror in your bathroom. That's a specular reflection. That gives you a very nice, crisp, clean, everything kind of comes right back at you. You can see yourself reflection. That's specular. When we have specular reflections in the body, we tend to get very bright, strong echoes. They usually appear white in our pictures. One that I think we can all kind of recognize is the diaphragm. The diaphragm is actually a pretty smooth muscle, and as the sound interacts with the diaphragm, we get this really bright white structure, and that's a specular reflection. Now, if the sound travels straight at the specular reflection, like in this top example here, that reflection is going to come straight back at the transducer. And so we can see some of it reflects back, some of that sound continues on. If we come at an angle to our specular reflector, that sound is going to head off in another direction. Some of it will kind of make it back to the transducer and we'll get some image from it, and we're going to learn more about this later too. But we're kind of setting the basis here that as the sound interacts with the specular reflector, again, some will reflect in another direction and some will continue through. So a specular reflection, remember, we have to have a smooth boundary. It is an organized reflection. We can predict relatively well where that sound is going to go. And it produces very bright white echoes on our ultrasound image. Now we talked about the other type of reflection being diffuse or backscatter reflection. So in this instance, you can think about looking at maybe a piece of aluminum. Aluminum's kind of shiny and it's smoothish. It reflects colors. We can kind of maybe make ourselves out in a piece of aluminum, but because it is not perfectly smooth like a mirror is, we get kind of this backscatter. So as the sound comes in and strikes this boundary, it kind of bounces around off that jagged border. And because of that, then sound gets kind of sent in a bunch of different directions. So with diffuse reflection, we have a boundary that is irregular, which is really most of the boundaries in the body. If you think about it, most of our organs are not perfectly smooth. They're going to be lumpy bumpy, or they're going to have different fat tissues going through them, or they're just irregular. So this is what most of our reflection is within the body. Again, when that sound comes in and interacts with that irregular border, it's going to be very disorganized. There's going to be no really rhyme or reason to where the sound gets reflected back to. Some will make it back to the transducer, some will just be sent off in a completely different direction. And because of that, because we're only getting a very tiny fraction actually returning back to our transducer, we actually see weaker signals. And that's where we get all the different types of grays on our image. We can equate the strength of the signal to the strength of the gray. And remember that because those irregular boundaries are kind of sending the sound in different directions, different irregular boundaries have different patterns of reflection. And that's why our liver looks a certain gray compared to our kidney looking a certain gray, compared to the heart wall, compared to what the vessels look like. So all the organs in our body have kind of these different boundaries. They produce different reflections, and that's how we're able to tell them apart. Now another cause of absorption is scattering. This is our second cause. And so scattering occurs when the sound beam encounters a smaller interface. So remember, reflection was larger interfaces, like 2 to 3 times the size of the wavelength. Scattering is going to be smaller interactions, and that's going to be more about the same size or a little bit less than the wavelength. And as the sound beam interacts with these smaller structures, it's going to disperse the sound in a bunch of different directions. So we can see in our example here, we have the sound coming in, and as the sound interacts with this small little structure, it's going to send a bunch of reflections all in different directions. They're going to have different intensities as they reflect off, with some of it coming back to the transducer. Now, one of the things that we know about scattering is that it is directly related to frequency. So the higher your frequency is, the more the scattering is going to occur, which means the less we're going to get more information back to the transducer. So a good one to think about for scattering is the lung. So the lung has tons of little tiny little air bubbles in it. It's got the itty bitty alveoli in it. And when the sound interacts with the air and these tiny itty bitty structures, the sound just gets burst out everywhere, completely unorganized, random directions. It just goes everywhere. And if you think about it, you can't see through lung, and that's why. And that sound isn't coming back to the transducer, it's just getting spent all over the place. And so that is why we can't see through structures that tend to cause scattering of our sound. Now there's a very special type of scattering that we need to know, and that's called Rayleigh scattering. And Rayleigh scattering occurs when the sound interacts with a structure that is much smaller than the wavelength. So just to recap again, specular was larger than the wavelength. Scattering in general occurs when it's about the same size as the wavelength. And then Rayleigh scattering occurs when you have something itty bitty and much smaller than the wavelength. And so that we're usually talking about is red blood cells. That's where we would see the Rayleigh scattering and red blood cells go together. And so with that, Rayleigh scattering does send the sound into different directions, but now it is actually very predictable. It's organized. It sends sound in the same direction, each direction, in multiple ways, in a very organized manner. Rayleigh scattering is also related to frequency, and it is related in the fact that the higher your frequency goes, the more Rayleigh scattering will occur. So they are directly related, and we can see that they're actually proportional to one another. So as our frequency increases, our Rayleigh scattering is going to increase by a factor or to the power of 4. So say our frequency doubles, then we're going to see a Rayleigh scattering of increase by 16. So that's 2 to the 4th is 16. So very high frequencies are going to cause a lot of Rayleigh scattering. And again, this has to do mostly with red blood cells. And the third and final reason for attenuation then is absorption. And absorption actually happens to be the #1 cause for attenuation. And that is because ultrasound energy gets converted into other types of energy, usually heat. And so when the sound interacts with the tissue in the body, the tissue absorbs that sound energy, converts it to heat, and then it just kind of dissipates and is no longer sound energy. So attenuation occurs because the body has sucked up that sound energy, made it into something else, and the ultrasound machine doesn't know what to do with heat. It's not a heat detecting tool, it's a sound detecting tool. So when the body absorbs that sound energy, makes it into heat, it's just energy loss to the machine, and we no longer can see. We see that absorption also increases with frequency, so they are again directly related. The higher your frequency, the higher your absorption is. So we just saw that scattering was directly related to frequency, and absorption is directly related to frequency. So that tells us now, again, that frequency has a lot to do with attenuation. As far as absorption goes in the body, think about two things that cause shadowing behind them. And that's typically because they have absorbed all of the sound energy. And again, there's just not enough energy to make any images behind it. So often we see bone or really dense structures like bone absorb a lot of the sound energy. Therefore, the sound attenuates very quickly. There's no longer enough sound energy to create images behind our bone, and that's where we get our shadowing. All right. So So remember, with attenuation, absorption, reflection, and scattering are the three reasons absorption is the strongest cause of attenuation. So when we are talking about attenuation, there is a concept called the attenuation coefficient. And basically what happens is, as that sound is traveling through the body, there are things affecting the sound. And we know its distance, we know its frequency, and then we just learned its reflection, scattering, and absorption. So with all these factors and no real way of determining how are those factors playing into this, we look at the attenuation coefficient to kind of organize and make it easier for us to understand how the sound is attenuating as it travels through the body. Now, the attenuation coefficient is typically reported in the number of decibels per centimeter of travel. Once we have determined what the attenuation coefficient is, then we assume it to be the same as it travels through the tissue. So again, just like our propagation speed in soft tissue, we've set that at 1540 meters per second. It's probably traveling at different speeds at different times, but we know the average is 1540 meters per second. Attenuation coefficient is kind of the same idea. We know it's probably attenuating more as it's traveling past bone, but probably and less during its travel through blood. But we're getting this attenuation coefficient to kind of give us the general idea of what's happening. So to calculate the attenuation coefficient, remember it's reported in units of decibels per centimeter. And we can use the attenuation coefficient multiplied by the distance to then calculate what is the total attenuation that occurs. So let's look at our example here. And this is just being told what the attenuation coefficient is with no real math to it quite yet. So our example tells us that the attenuation coefficient is 2 decibels per centimeter. So we know as our sound travels into the body, it is going to weaken by 2 decibels for every centimeter that it goes in. So we can then assume that at 5 centimeters, the total attenuation that has occurred is 10 decibels. And that's because we took 5 and multiplied it by our attenuation coefficient. At 10 centimeters then, we know that the total attenuation that's occurred is 20 decibels. So let's take a look at this on the whiteboard. So here is our, oh, that marker's not working. Grab my pink one again. Here's our transducer, and it is sending sound into the body. And so we've got, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. We'll call these centimeters into the body. All right, and we were told that the attenuation coefficient equals 2 decibels per centimeter. So that means for every centimeter, we are decreasing by 2 decibels, going down. Okay? And to figure the total attenuation that occurs, we need to take the distance, like 10 centimeters, and multiply it by our attenuation coefficient. So at 10 centimeters, the total attenuation that has occurred is 10 times 2, or 20 decibels. At 20 centimeters, then we can do the same thing. Total attenuation would be the 20 times 2, it's the distance, times the attenuation coefficient. Total attenuation at that point would be 40 decibels. And then we can go back to what we learned about attenuation and negative decibels. A minus 3 decibels is half as strong, and a minus 10 decibels is 1/10 as strong. So we can kind of evaluate this even further. We know there's a 1 or minus 10 here. We know there's a minus 10 here. So that's a 1/10 and a 1/10. Multiply those together. We can now see that at 10 centimeters with this attenuation coefficient, at 10 centimeters, the signal strength is 1/100th of what it used to be. And we can do the same idea down at 20 centimeters. We know we have those changes of -10 decibels, right? Each one of those is a 10th as strong. So at 20 centimeters, the signal is now 1/10,000th as strong. So we probably have almost completely attenuated at that point compared to what we were. All right, so the attenuation coefficient just kind of gives us a general idea, how weak is this getting per centimeter of travel. Well, then you might be asking, how do we know what the attenuation coefficient is? Well, you're in luck. There is an attenuation coefficient formula for when we are dealing with soft tissue. So remember that these formulas are only applicable to soft tissue applications, okay? And that's what we're dealing with ultrasound, so it all works out just fine. But in soft tissue, we can see then that the attenuation coefficient is going to be our frequency in megahertz divided by 2. Or another way to look at it then is to say that for every megahertz that our transducer has, it is going to attenuate by 0.5 decibel per centimeter. So if you remember earlier, I mentioned we were going to see the math on why when frequency increases, attenuation increases. Here it is. This is it. This is what tells us that there's more attenuation when our frequency increases. So let's look at the example over on the whiteboard again. So we just learned that the attenuation coefficient is the frequency divided by 2. And I'm going to drop out the units just for sake of making this easier to write. Or we can consider that the attenuation coefficient is going to equal 0.5 decibel per centimeter per megahertz. Okay, so in our example on this slide, we are given that the frequency of the probe equals 7 megahertz. So we can do 7 times 0.5, or we can do 7 divided by 2. It's really the same either way. And either way, we get 3.5 decibels per centimeter. So again, if this is our transducer, 1, 2, 3, 4, we'll just go down to 5 centimeters. For every centimeter, we are decreasing by 3.5 decibels. Okay. And if we go back to our, I'm going to pop it up here real quick. If we go back to our formula here, we know then that the AC multiplied by the distance gives us the total attenuation that occurs. So now, if all we've been given is the frequency of the probe, we can calculate the attenuation coefficient, knowing what it is in soft tissue. If we know the distance then that the sound has traveled, we should be able to calculate the total attenuation. So using this example again, we can see then at 4 centimeters, 4 multiplied by 3.5 gives us 14 decibels of attenuation. At 6 centimeters, going to just be 6 multiplied by 3.5, we have 21 decibels of attenuation that has occurred. So again, you'll get some practice in doing this in your workbook as well. Write down these two equations if you're keeping a list of equations handy. Now again, that formula only works for what we assume to be soft tissue. And remember, soft tissue is just a general term for what the sound will be traveling through. There are times where it'll be very obvious that the sound is traveling through different structures, say like the heart chambers or the urinary bladder or the gallbladder. And that is going to change what the signals look like behind them. And so we see that water has a very low attenuation rate. Blood, urine, biofluids also low, fat very low. So we're going to see more of that sound energy being able to continue through versus it being absorbed like it does with bone. This is a big reason too then why we use water-based gel for our ultrasound coupling, and we're going to learn more about that in chapter 8, I believe. But we want to use something that helps us get the sound beam into the body. So we see here that air is extremely high in attenuation. So if we just tried to use our transducer directly onto the skin, there's going to be itty bitty pockets of air in there. That's air. That air is going to attenuate our sound, and we're not going to get any images because the air took up so much of our attenuation. So we use a water-based gel because it's not going to affect any attenuation that's coming out of the transducer. It's not going to affect the sound that's coming out of there, and that's going to direct it into the body so the attenuation can happen in the body, not before it even gets in there. So from this chart, all I really want you to know is that why we use water-based gel to help us get our images. Know then that these items that have the little bit more liquidy type basis to them is going to have a little bit more of a low attenuation rate, where our more solid things are things that are going to scatter or absorb the sound beam are going to have higher attenuation rates. Another topic that we need to consider when we're talking about attenuation then is called the half value layer thickness. So it has a couple other names. Again, remember, anything that has other names is perfect board questions, or they'll throw them in, what's the penetration depth of this, instead of calling it the half value layer thickness. So know your alternative names. So it can be also called penetration depth, depth of penetration, or the half boundary layer. And what the half value layer thickness is just another way to look at attenuation. And what it tells us is how far does the sound beam need to travel before it is half as strong as it was. So it is a distance measurement, and in ultrasound it's typically between 0.25 and 1 centimeters. So that tells us that in the first quarter to 1 centimeter, our sound beam coming from the transducer is already half as strong as it was. So that really tells us how sensitive our machine is to very, very weak signals that are returning. So half value layer thickness is going to depend on two things. The first one is the medium, and the second one is the frequency. Remember, half value layer thickness is telling us about how far the sound has to travel before it attenuates to half as strong, correct? Right? And we know that attenuation has to do with frequency, so that makes sense. And we saw on that chart a couple slides ago that water doesn't cause nearly as much attenuation as, say, bone does. And so it does depend on the medium and the frequency to tell us how far something needs to travel before it is half as strong. So in media, such as bone, that has a lot of attenuation, the half value layer is going to be very thin. So it's going to be 0.25 centimeters, 0.1 centimeter. On the opposite side of that then, in media that has very little attenuation, such as the urinary bladder, the half value layer is going to be very thick. So maybe it's more like 4 centimeters, 5 centimeters. So with knowing that the medium and the frequency have to do with the half value layer thickness. We can see that they're related and that attenuation will increase when our half value layer thickness is thin. So again, attenuation increases in bone, half value layer thickness of bone is very thin. And then frequency also has to do with it, because we know that the higher the frequency is, the more attenuation that occurs. If more attenuation occurs, then it's going to get to that half value layer thickness much quicker, which again makes it inversely related. So our frequency increases means that our half value layer thickness will decrease or be very thin. So another way that I kind of like to think of the half value layer thickness is if you think about reading a book. Think about your physics book and you're reading it, and you know before you start sitting down to study that physics is boring, you don't really want to read your book, so you kind of read it slow. And that would mean that maybe you can read 100 pages in an hour. I have no idea if that's slow or not. Anyway, so 100 pages in an hour, you know, is your speed at which you can read. So you could do the math. How long will it take you to read halfway through that book? All right. Where as opposed to a book that you really enjoy, maybe you could read 200 pages in an hour. And so you know that that book that you really enjoy, the book that has a lot of your attention or a lot of attenuation, is going to have a thinner time. You're gonna be able to get through that book sooner, quicker, and you're gonna be halfway done with it much speedier. Same idea with the half value layer thickness. When you have a material that absorbs a lot of the sound, your half value layer thickness is going to occur much sooner than it is with something that does not absorb the sound as quickly. So let's take a look at an example with the math on this. So let's take a look at some examples of half value layer thickness and how to figure it out. So I've got the example up here, but I'm going to go to the whiteboard and I'll kind of read it to you as we go through to kind of figure this out. So our example tells us that the attenuation coefficient equals 1 decibel per centimeter. And so what that is telling us is that for every centimeter that the sound travels into the body, we are going to lose a decibel of sound, right? So we're minus 1, minus 1, minus 1, minus 1, minus 1 for each centimeter that we travel into the body. What half value layer thickness is trying to ask us is what is the depth, how many centimeters do we travel before we get to attenuation of 3 decibels or negative 3. So what is the depth that we get to? So we can look at our chart here and we can just count them. 1, 2, 3. At 3 centimeters, we have lost 3 decibels. And so now we are half as strong as we used to be. So if you make a chart out like this and kind of count the numbers down, add them up, that's one way to do it. Otherwise, the other way that we can do it is to take, knowing that our 3 decibels is the change that we need to get to half as strong, we can divide that by our attenuation coefficient. The decibels cancel each other out. 3 divided by 1 equals 3 centimeters. And that's it. That is how you figure out your half value layer thickness. Let's do another example. Let's change our attenuation coefficient to, let's make it 2 decibels per centimeter. And again, we're trying to figure out our half value layer thickness. So we can very easily figure out 3 divided by 2 equals 1.5 centimeters. We can double check that then with our chart. So I'm going to make little lines, big lines here. And so we know these are all centimeter marks. And we know that for every centimeter, we're down 2. And why I'm showing you the other math way of it, because if you'd like the chart to figure it out that way, I think it's a great visualization. But look at 1 centimeter we had 2, and at 2 centimeters we jumped to 4. And so we're like, oh shoot, well we need where we get to that 3 decibels. 4 is too big and the 2 is too small. So that is where doing the math this way helps us out, but then we can always double check it divided by the 2. Let's do one more example. And this is the other example that's listed on your slide there. This one we have the attenuation coefficient is kind of big. It's at 15 decibels per centimeter. And so again, we want to know what is the depth that we are -3 decibels. So we can easily just take our 3 and divide it by 15, and that gives us 0.2 centimeters is our half value layer thickness. Now again, if you are the type that wants to draw out your chart and look at it that way, another thing that we can do then is write this a little bit differently. We can make 15 decibels per centimeter the same as saying 1.5 decibels per millimeter. And so that number maybe works a little bit easier. Remembering that these are millimeters, then we're -1.5 for each millimeter. We can then see at 2 millimeters, we have reached our 3 decibel attenuation. So 0.2 centimeters is the same as saying 2 millimeters as well. So just a couple different ways to kind of tackle the half value layer thickness. Remember, it is at what depth do we get down to a -3 decibels. Another term that has to do with how sound interacts with the media is called impedance. And impedance is also known as characteristic impedance because it has to do with the makeup of the media and how the sound then will interact with it. So impedance is calculated, underline that, impedance is calculated, and it's a value that represents the acoustic resistance to sound traveling through a medium. So how does that media try to kind of stop sound from traveling through it? So media that has very low impedance allows the sound to travel through it very easily. Material that has very high impedance would try to stop the sound from traveling through it very easily. So impedance is the resistance to sound traveling through the medium. It is expressed in units of Rayleigh, which is represented by a capital Z. And in ultrasound, our typical values are 1.25 to 1.7 megarayleigh. And this is 100% going to be determined by the medium. Now the whole reason, again, that we have ultrasound images is because the tissue in our body is made up of different impedances. So the liver has a different impedance than the blood vessel wall that's traveling through it, which has a different impedance than the blood that's actually traveling through that vessel, which has a different impedance than the other wall of the blood vessel. You kind of get the idea. Anything that we can see on our ultrasound machine is there because it has a different impedance to the structure that is immediately adjacent to it. When there are very strong impedance differences, say between the liver and the diaphragm, we get very bright reflections. We get more reflection at that level. When more transmission occurs because there is a low impedance difference, we're going to get lower levels of grays. And the only reason we get a reflection is because impedance is different. If the impedance of two structures is the same, we're not going to get a reflection back. You have to have a change in impedance. So here we have again another formula. The impedance formula you're going to be using for your workbook, so I would write this down. I think in general, what you need to gather from this formula is that impedance is dependent on the medium, because it's the density of the medium and the propagation speed, which we know is medium based as well. So it has everything to do with medium because of these two factors, the density and the propagation speed of the medium. Okay, and like I said, you are going to be using this formula when you work through your workbook. All right, moving on to incidence. So incidence is the angle in which the sound beam strikes a boundary. We call that the angle of incidence. And we have a couple different ways that the sound can interact with boundaries. It can hit it directly at a 90-degree angle, and so we call that a right angle, or at 90 degrees, or it can come in obliquely. And obliquely is literally anything other than 90 degrees. And if the incident angle is less than 90 degrees, we call those acute angles. If it is more than 90 degrees, we call it obtuse angles. So again, if this is our boundary and my angle is coming in directly at it, we're at 90 degrees. This is that right angle, or the right, or right, yes, 90 degrees or right angle. We can then have an acute angle, or we can have an obtuse angle. And that's, again, anything other than 90 degrees is not a right angle. We call it oblique. So when we talk about normal incidence, we are talking about that 90 degree, that right angle of incidence. So normal incidence comes in at a bunch of different other names. We have perpendicular, orthogonal, right angle, or 90 degrees. All of those are the same thing. They mean normal incidence. So this is a big one where I know I've seen, it'll say something like, what is the result of perpendicular incidence on this media? Or what happens when there's an orthogonal incidence? You have to know that those mean normal and that they mean at 90 degrees or at that right angle. Contrary to that, then, we have oblique incidence, and that again literally means anything other than 90 degrees. Thankfully, oblique incidence does not have a bunch of names, so they have to say oblique incidence. So that's kind of my tip for that one. If it says oblique incidence, or I guess maybe non-perpendicular, which is kind of a silly qualifier, but oblique incidence is anything other than 90 degrees. Remember those other terms for normal incidence. And as we've been talking about through this whole chapter, the whole reason that we get ultrasound pictures is because some of the sound is reflected, and the reason that we get more ultrasound pictures is because some of that sound transmits and then gets reflected, transmits, reflected all the way through the depth until it attenuates completely. So we need to talk about what happens when sound strikes a boundary. What is its incidence? What is the angle that it's striking that boundary? And then what happens to the sound that gets reflected, and what happens to sound as it gets transmitted. So first, we are going to talk about incident, reflection, and transmitted sound in general. So here we have, just in general, incident intensity, reflected intensity, and transmitted intensity are all related, and they have to conserve energy. So we have an intensity coming into a boundary. We're just gonna use a general number, 50. 50 watts per centimeter squared. That's our coming in intensity. Our reflected intensity plus the transmitted intensity has to equal 50. And that's because energy cannot be created or destroyed. We're conserving energy. So this is another formula that I would write down. It really just kind of gets to the core that energy must be conserved. Now there's another idea of intensity coefficients, intensity reflection coefficient, or we'll see that abbreviated down to the IRC, is the percentage of the intensity that bounces back after the sound hits a boundary. The amount of energy that bounces back is actually very, very little, usually less than 1% in diagnostic ultrasound. It is even lower when the boundaries are very similar, and then it's very high when the boundaries are very different. So let's just think about that. So we have our boundary here, and let's say this boundary is, let's say this is fat, and let's say this side is skin. And so when the sound comes in to that boundary, some of it is going to be reflected, most of it is going to keep going through. And so the IRC tells us what is the percentage of the amount that was reflected. What is the intensity reflection coefficient? And again, let's say that this is 50 watts per centimeter squared coming in, and let's say our reflection coefficient is 1%. That means that only 0.5 watts per centimeter squared is going to head back to the transducer. The rest of it, the 49.5 watts per centimeter squared, is going to keep going forward in through the fat. And then this is going to strike another boundary, and then some will get reflected, a little bit more will keep going, that'll strike another boundary, and it just kind of keeps going. So the incident intensity must equal the return and the transmitted intensity. And the IRC refers to the percentage that comes back. And we're going to learn that the IRC and the ITC, or the intensity transmission coefficient, which is the percent going forward, are also going to need to equal 100%. So just to reiterate, incident intensity must equal return intensity plus transmitted intensity, and the reflection coefficient, the IRC percent, plus the transmitted coefficient percent must equal 100%, because again, energy is being conserved in here. So again, intensity equals the return intensity plus the transmitted intensity. 100% will equal the IRC plus the ITC. Intensities are again in watts per centimeter squared, typically. The coefficients are percentages. They are unitless numbers. And remember, in ultrasound, very, very little is returned. We're talking less than 1% is returned, where about 99% is going to keep moving forward. So let's talk a little bit more then about how media interacts with one another in the realm of normal incidence. And remember, when you hear normal incidence, you're thinking straight on, 90 degrees, perpendicular, orthogonal, all the same. So when we hit a boundary at 90 degrees, it is striking at normal incidence. For reflection to occur, there must be a difference in impedances. Remember that that's the media part of it. The media has to have a different structure to it to return a reflection. The reflection that occurs then is dependent on the difference between the impedances. So in our chart on the bottom here, we can see no reflection occurs when the impedance of media 1 equals the impedance of media 2. There's going to be no reflection. All of the sound is just going to keep traveling. It's not going to recognize that anything is happening. And again, this is with normal incidence. When there's a little difference between media 1 and media 2, we're going to get a small reflection. So if there's not a huge difference, we get just a little bit of reflection back. When there's a big difference between the media, we're going to get a large reflection back. And if you haven't guessed, there's math to go along with it. So remember that Z stands for Rayleigh, which is the calculated impedance. And we can plop in impedance into our formula here to see that. So let's take a look at a couple examples. So I'm going to write down our IRC formula. So Z with the little 2 on the bottom, that's media, the impedance of media 2 minus the impedance of media 1. And that's all over the impedance of media 2 plus the impedance of media 1. Whatever answer you get from that then is all squared, and then we're going to multiply it by 100 to get our percentage. Pull that down a little bit here. All right, so let's plug in some numbers. Let's first take a look at when the impedances are the same. So let's say media 1 is 5 rails and media 2 is also 5 rails. So we can put 5 minus 5 is 0. 5 plus 5 is 10. We would take all of that squared. Well, if you remember from math, 0 divided by 10 equals 0. And, or 0 divided by anything will equal 0, and 0 squared equals 0. And 0 times 100 equals 0. So this is telling us that the IRC percent is 0%. There's going to be no reflection occurring. We just proved it because our media impedances are the same. Okay? So no reflection occurs in normal incidence when the media impedance is the same. Let's take a look though when they're different. So let's say media 1 is 5 rails, and let's say media 2 is 10 rails. All right, so now we have 10 minus 5, which is 5. We're going to divide that by 10 plus 5. So we have 5 divided by 15, and we're going to square all of that. So we can take 5 divided by 15 and then we square it. So 5 divided by 15 is 1/3. 1/3 squared, then we get 0.1 repeating. We'll multiply that by 100. And so our final is about 11%. So our IRC with a difference of 5 rails is about 11%. So I'm going to leave these numbers here and we'll put the 11% by it so we can see how this compares to medias that have really big differences. So remember, when they were kind of similar, there's a little reflection. When they are very different, we get very big reflections. So let's say again that media 1 is 5 rails, and let's say that media 2 then is, let's do 40 rails. So now we have 40 minus 5 equals 35. And then we have the rails added together, so we get 45 on the bottom there. So we have 35 divided by 45, all of that squared. So 35 divided by 45 is 0.777 repeating, and then we're going to square that, and we get 0.604. We'll multiply that by 100 and we get 60%. So look at, remember when they were equal, we got 0%. When there's a small difference, we got 11%. And when we had a large difference, we got 60%. So that again is just showing us how when the media impedances are different, they change how much is reflected. So then we know that we can take these IRCs, these reflection coefficients, and we know then that the IRC plus the ITC must equal 100%, right? So if 11% is being reflected, then we know that 89% is still traveling into the body. On this one, if 60% is being reflected, then 40% of the beam is still going into the body. So that is how impedance and reflection and transmission are all kind of related to one another. And remember, this is all with normal incidence, 90-degree orthogonal perpendicular incidence. So this just kind of goes back then to the other side of the IRC. If we're looking at what the IRC is and a little or a lot is being reflected, then that's going to affect is there a little or a lot being transmitted. So again, if the media are the same, all of the sound is going to be transmitted. If they have the same impedances, all the media or all the sound gets transmitted. If they have little differences, then there's going to be more transmission. If they have big differences, there's going to be less transmission. So if we look at the IRC, knowing that IRC plus ITC has to equal 100%, then we can kind of look at normal incidence and look at what it does to the transmission. Again, we know if the media have the same impedances, then all of the sound is going to be transmitted because none of it was reflected. If there's a little difference between the media, then we know that there's going to be more transmitted because very little of it was reflected. And if there's a big difference in the media, then we're going to have less transmitted because most of it was reflected. So it's just kind of the opposite viewpoint of what is happening at that boundary. And as I had showed you before, just taking the intensities and dividing it helps us to figure out the ITC, or it's as simple as figuring out what the IRC is. Knowing that IRC plus ITC has to equal 100%, you can just figure out the other variable then. So remember, all of that was with normal incidence. We're now going to talk about reflection and transmission with oblique incidence. And you basically have to forget everything I just taught you. Literally. Like, yes. And I know that sounds crazy, but all those formulas only work with normal incidence. When we start talking about oblique incidence, turns out we don't have fancy formulas that are super easy just to plop some numbers in and then we figure out everything that's going on. And that's because oblique incidence is unpredictable. We don't know what's going to happen. You know, when we were talking normal incidence, we said that if the impedances are the same, nothing happens. With oblique incidence, it might happen, it might reflect, it might not. It might reflect a lot, it might reflect a little. We have no idea. So it's just very hard to predict what happens to the sound beam when we come at a boundary at an angle. And unfortunately, if you think about it, that's what most of our sound beaming is. It's at angles. So most of our sound beam reflection and transmission is unpredictable in the ultrasound realm. However, we do know a couple things about oblique incidence. And the first one is that reflection can't be calculated or predicted. However, there are two rules that apply to reflection. One is conservation of energy, and that the reflection angle is going to equal the incident angle. Right? So these are very two big things that we know about reflection with oblique incidence. So if we look at the conservation of energy, again, we know that the amount of energy that is coming into the boundary whatever is reflected has to equal that plus the transmitted part has to equal 100% still. We're not going to destroy or create energy even though we're coming at an oblique incidence. So that rule is still true. The other rule then is that the reflection angle must equal the incident angle. So when we are coming in at an angle, that oblique angle, if we were to put like a perpendicular line here or a mirror, then we would see that as that angle comes in, it's going to bounce off at the same angle. So this is our angle of incidence, and then we have our angle of reflection. And with oblique incidence, we know that these must be equal. Now, as far as transmission with oblique incidence, again, we can't predict it. It can't be calculated. There's no fancy formulas for us to just put numbers in and figure it out. If sound beam is transmitted, again, we don't know if it's going to be or not at any oblique incidence, then what's going to happen, it's going to do one of two things. It's either going to travel straight ahead or it's going to refract. So we can talk a little bit more about refraction then. So refraction only happens when two things are true. The first one, there must be oblique incidence. That's why we're talking about it right now. There must be oblique incidence for a refraction to occur. The other thing that needs to happen is propagation speeds must be different. Must be different, okay? So if these two conditions are met, then sound is never going to travel straight forward. It is going to change directions or refract. And just kind of like what we learned with normal incidence, when there is a small difference in propagation speed, the refraction is smaller. And when there's a large difference in propagation speed, the refraction will be bigger. Now, there is a little bit of math to go with this, and I'm going to leave a couple slides here for you to read about. We'll talk about them too. But I don't want you to get hung up on Snell's law whatsoever. Just know that Snell's law is the reason why refraction occurs. That if we're going to break it down to one thing, that's the one thing you need to know about Snell's law. And so basically what it's saying is that the angle that we're coming in at, the incident angle, the angle that we're coming in at, will change in its greatness or the steepness of the angle depending on the difference in the speeds. And Snell's law is basically just a number from 0 to 1. It actually kind of helps us to graph out circles into a straight line, which is trigonometry and again unnecessary for what we need to know about physics, but look, it kind of looks the same. We'll talk about cosines later when we talk about Doppler equation, but it's all kind of related. More information in here that you need to know. All you really need to know is that the greater the differences in the speeds of the media, the greater the change in the angle of refraction. Okay, we're going to move on. So knowing that Snell's law predicts the changes of angles, let's break it down to some very basic concepts regarding it. Okay? So when your speed of media 1 is the same as the speed in media 2, and we have oblique incidence, transmission is going to be straight ahead. The angle is straight through. Compare that to then when the speed of media 1 is less than the speed of media 2, we are going to have a smaller angle of incidence than the angle of transmission. Compare that to a third scenario. When we have the speed of 1 being greater than the speed of 2, our angle of incidence is then going to be larger than the angle of transmission. So let's take a look at this. So here's our boundary. Remember, we're coming in at an angle. We've got the oblique incidence going through, right? And when we have oblique incidence, we know that our reflection is going to be the same angle back. These angles are the same. They are equal. That's what happens with reflection. That's the only thing you need to know. Angle of incidence equals the angle of reflection. Okay? Transmission is where it gets a little tricky. If we have, I should point out too, oblique incidence has to do with the propagation speed. Okay? Normal incidence was impedances. Oblique incidence is propagation speed. So if the propagation speed, we'll just say, is 10 meters per second for both, if they are equal, our transmission is just going to keep going forward. There is no change in the angle. This angle is the same as this angle. Okay? There's no change when our propagation speeds are the same. When our propagation speed are different, then that transmission angle is going to change. So if our propagation speed of media 1 is less than the propagation speed of media 2, so let's make that, we'll just say 20, then our angle, our incident angle, is going to be less than our transmission angle. This is smaller than this angle. So it's going to bend that sound beam in a completely different direction as it travels through. The other thing that we learned is that when these are very similar, we're going to have less bends. So if this is, say this is our, everything's equal, these are relatively similar, we're going to have kind of the same bend. If these were drastically different, let's say 100, we're going to get a big bend of that sound. But either way, this angle is going to be greater than the incident angle. We can look at that in another way then too. Let's change this up. What happens when our second speed is less than? Let's say we're at 50 and our new speed is 40. So now our incident speed, or incident side, is faster than our second media. We're still coming in at an angle here to our boundary. Remember, if they were equal, they would completely travel in the same direction. There would be no refraction, but they're not equal. And so in this case, our angle is going to be less. This angle is less than this angle. So notice that this greater than matches up with this greater than. When it was the other direction, they also equaled the same direction. So that's another good way to remember it. If these changes were even bigger, say this one was 10, then we would get even a steeper degree of change. Okay. So let's just go through that again just one more time, because this is a very important concept when we're talking about the angles. I'm trying to pull out a different color here so we can see things a little bit better. So this is our boundary line. This up and down one here, this is our boundary line. Remember that this is our incident angle. It's coming in at an angle. Our reflection is going to have the same angle coming back. That just happens. automatically, so these angles must be the same. The difference comes in with the transmission and what the propagation speeds are. So if our propagation speeds are equal, if they're equal, our propagation speed is going to, or excuse me, if our propagation speeds are equal, our transmission angle is the same. It's going to travel straight through, no change in direction. If speed 1 is less than speed 2, so if we're less than, we're going to get an angle that looks like this. And that's because this transmission angle is going to be greater than the incidence angle. The opposite of that then is when speed 1 is greater than speed 2. We're going to get a bend that looks like this. And that's going to tell us that this angle is now less than this angle. Okay? So the biggest thing I can tell you to look for is that these match up. This tells us that this angle should be bigger than this angle when this speed is bigger than this speed. The green ones match up too. When speed 1 is less than speed 2, then angle of 1 is less than angle of 2. And you'll get some more practice with this in your workbook as well. And that, everybody, is the end of chapter 6. So a lot of really different concepts, but I hope you can kind of see how they all are sort of related. You know, we talked about logarithms and decimals and the attenuation coefficient. That half of the chapter all kind of went together really nicely. And then the impedance and the IRC and the ITC and all of that, how we figured that out, all kind of went together as well. But in the end, it's all about how sound is interacting with the media. Is the media absorbing the sound, making it attenuate, or is the media different densities or different impedances and changing the amount of reflection that's happening, or are they different propagation speeds and changing the direction that the sound is traveling? So try to find some of those patterns, some of those congruencies that you can see within the book to try to relate these concepts to one another. And then again, just practice these concepts, write them down in different ways. Look on YouTube for other media that you can watch to help explain it again in a different way. If you hear it a different way, it might make more sense. Read your book again, find that other media, come back to this, do your workbook. The more effort that you put into this, the more it's going to kind of stick in your mind, and it's going to feel much less overwhelming when you get to your quizzes or when you get to your boards. All right. So please let me know if you have any questions. I will be happy to add more media if we need something explained in a different way. Otherwise, have a fantastic week and really take your time with this chapter. There's a lot of concepts that we're covering.